Today is the last lecture, and I will talk about some open problems and some confusing directions that I myself do not fully understand, and hopefully people who come after us will clarify this. So there's going to be a few disconnected subjects, and I will start with something which I can call symmetry meaning of leaders. So recall that our logic was that I introduced this Cardy field transformation, which takes the n fields in the replicated basis and makes a linear transform. Phi 1 is curly phi plus omega over 2, and then the other phi i's are phi minus omega over 2 plus chi I for I from 2 to n. And then with this Cardy transform, I can transform the replicated action Sn, which has Sn global symmetry and which has the form sum over I from 1 to n 1/2 d phi I squared plus v of phi I minus delta over 2 phi 1 plus phi n squared. So with this Cardy transform, we mapped this Sn action on something that that one can call pre-SUSY action, and which has the following form. So it's d curly phi d omega plus 1/2 d chi I squared minus delta omega squared over 2 plus interaction terms which have the form omega v prime of curly phi plus chi I squared v double prime of curly phi. And now if I take this pre-SUSY action and if I further make the replacement of chi's by the fermionic fields psi bar and psi, I land on the Parisi-Sourlas supersymmetric action. So I call this action pre-SUSY because it involves this scalar fields chi I. There are minus 2 scalar fields chi I. So it becomes SUSY after I map this mapping, after I do this mapping. So one open question is, what is the symmetry of this pre-SUSY action? So you see, I know what the symmetry is after I make the mapping to the SUSY variables. It becomes supersymmetry. But it's reasonable to think that there should be some trace of the supersymmetry even before I do the mapping. Even at this level of the fields phi, omega, and chi I, there should be some symmetry. But I'm unable to find an expression of the symmetry in terms of variables phi, omega, and chi I. So the only way that I can understand the symmetry is to map to the SUSY variables. And that's pretty annoying, because for recall that last time we introduced this classification of leaders, and they were SUSY writable leaders, SUSY null leaders, and non-SUSY writable leaders. And the SUSY writable leaders, their properties, they can be studied in terms of the Parisi-Sourlas supersymmetric action. But the properties of the SUSY null and the non-SUSY writable leaders, they have to be studied on the level of the pre-SUSY action, because they cannot be mapped to the SUSY variables. And of course, if you work with an action, you would like to know what its symmetry is because it controls all the calculations. And yeah, and we don't know what the symmetry is. Now, if the symmetry is clarified, then it would have important consequences also for understanding the symmetry meaning of leaders. That's the question that I would like to ask. So let me explain. Recall that last time we said that any SN singlet interaction after mapping to the Cardy variables, it can be written as a leader, which is the lowest dimension part, plus followers, F1 plus F2 plus dot dot dot. And then I made a basic premise, so I argued that it's enough to look at the anomalous dimensions of leaders. So I can forget about followers, and it's enough to look at leaders. And what does it mean to look? Well, it means that I was studying the following problem. I was looking at the action which was the perturbation of the pre-SUSY action by a bunch of terms. I would perform this, I would deform this pre-SUSY action by a bunch of leader couplings. And I just used this deformation to study the anomalous dimensions of the leaders, so it's enough to assume that all these leader couplings are infinitesimal. And then I study how these couplings change under the renormalization group flow, and if they grow, it means that the leader is relevant. If they decrease, it means that the leader is irrelevant, and so on. So that's what I do. And for this picture to make sense, to be consistent, one has to have the following basic property, that leaders under the renormalization group flow, they only generate leaders. So I start with this Lagrangian, I make a renormalization group step. I would like to be able to rewrite my Lagrangian after renormalization group step in the same way, with just changed couplings GI. So leaders under RG, they should only generate leaders. And actually, our calculations show that this is indeed the case. So if you compute Feynman diagrams for vertices coming from leader interactions, so leader interactions, they involve some particular linear combinations of operators, you find that if you do an RG step, you never find you only find combinations where again which correspond to leaders. Yes.
Using dimensional regularization.
Using dimensional regularization.
But dimensional regularization, there is no way you could generate operators that have a lower dimension. Let's say renormalization group flow.
Yeah.
No leaders that have dimension which is higher compared to leaders.
Yeah.
So for them to be generated, you have to have quadratic and higher divergences.
Yeah. But it's not as trivial as that, because it's true that leader is the lowest dimension part, but it has several this linear combination. So leader itself is a linear combination of several operators which have the same scaling dimension with very precise relative coefficients. So what you would like to see is that after you do renormalization group step, these relative coefficients just get rescaled by the same number but do not change.
Ration
should remain the same.
I thought you meant probably a misunderstanding. You said that you don't want to have followers to be generated through renormalization group flow.
What you could generate is a follower of another operator.
No. Leader.
Yeah.
What I was saying is if you have leaders, so you go to renormalization groups procedure. If you're using other equalization rather than dimensional derivation, the difference is that you could generate contribution which correspond to operators with higher dimension.
What I want to say is the following. So you have a leader here of one operator, and then, for example, there is another operator which has a lower dimension leader. And then for that operator on this level, there is a follower. This follower has the same dimension as the leader of another operator. So you would like to make sure that once you start realization group starting from this leader, you're not going to generate followers of some other guys. And according to our computations, this never happens. To one loop, to two loop that we check, this never happens. So there must be a symmetry reason for that. So we know that this property, that certain operators do not generate other operators. This happens if these operators are singlets under a certain group. But what is this group? To know the answer to this question, we have to understand the symmetry of this pre-SUSY action. Sorry, there was also a question for me.
No, I was just going to ask about precisability.
Yeah.
So it's orthogonal to the question of whether it's SUSY writable and so on. So because you explained your constraints depending on which operators could be with SUSY writable and so on. But here L1 and F could be either SUSY writable or not, or L is always SUSY writable, but no.
This question, of course, if this guy, for example, is SUSY null, then it could only mix with followers which are also SUSY null, but there are such followers which are SUSY null, but they are not generated. So we don't know the full answer to this question, but we know this answer only in one case, which is for SUSY writable leaders. So if we have SUSY writable leaders, for the SUSY writable leaders, we can analyze them in terms of the Parisi-Sourlas SUSY action. So at least we know what our symmetry is. The symmetry is the Parisi-Sourlas supersymmetry. But the question still makes sense. So take a SUSY writable leader. It's just some particular supersymmetric operator. You do an RG realization group step. You will find always only leaders. So it means that within the supersymmetric theory, the SUSY writable leaders, they should correspond to some particular class of symmetric operators. What are these symmetric operators? So we have found the answer to this question. So these are the SUSY writable leaders are precisely operators of SUSY theory which are super translation invariant and SP2 invariant. So SP2 invariance just means that it should involve psi bar and psi in symmetric combinations. So this is a non-trivial. This is not a fully trivial fact. So the super translation invariance corresponds to this transformation. So d phi equals epsilon psi bar plus epsilon bar psi. D psi bar equals epsilon bar omega. D psi equals minus epsilon omega, and d omega is equal to 0. So now, given any operator written in SUSY fields, you can check whether it's invariant or not in these transformations. For example, phi omega plus twice psi bar is invariant. And so if you see such an invariant operator, the claim is that it will necessarily come as a leader of an ascent singlet. So that's not a trivial fact, but in fact, in this case, you can check that this operator is a singlet coming from, so this comes from sum of phi I squared from 1 to n. So this is a leader of phi I squared.
Sorry, so this is the highest component of the SUSY multiplier.
Yeah, so super translation invariance, it's equivalent to say that it is x theta theta bar for some superfield x. It's totally equivalent. And so in this case, this question has a neat answer. Why leaders only generate leaders? But in more general case, we don't know. So it's a simple question, but I would like to know the answer to it. So as I said, it's going to be several disconnected topics, and that's the end of the topic. So, I was also hoping that we could do a little bit of brainstorming. So if some of you has any ideas how this could be approached, then please shoot. Yeah.
I have a question actually, because when you describe whether an operator is writable or not, you said you replace chi by this Fermi bilinear.
Yeah.
Is that literally the operation that you do, or like, do you understand if I give you any operator, what are the rules?
Yeah. We have a full set of rules. So the rules go. If you have, the rules, for example, particular cases are chi squared goes to twice psi bar psi, and d chi squared goes to twice d psi bar d psi. But these are just two examples of a general rule that we have, which, given any operator which is in which chi enters in ON minus 2 invariant combinations, there is like a very specific rule which tells you how to which operator in terms of psi bars and psis you are supposed to map it.
But these are just rules, right? There's no field redefinition or something like that, because you know that you cannot do this to any operator. So it's some.
These are rules which these rules are defined according to such. So these are rules, but the rules are not arbitrary. The rules are such that any operator on the left-hand side, it's an operator of the Parisi-Sourlas theory. It has certain correlation functions, which you can compute from the Lagrangian of the Parisi-Sourlas theory. And so the claim is that after this mapping, the correlation functions remain invariant.
So does this mean that there's actually a field redefinition that maps the two theories, or?
Well, not really, because, for example, there are other operators in the Parisi-Sourlas theory. If, for example, take a correlation function of Parisi-Sourlas theory, which is of this form: chi I1 at some point x1, chi I2 at some point x2, 3 and chi I4 at 4 different points and with 4 different indices which are not contracted. This correlation function cannot be mapped to the SUSY theory and cannot be computed from the SUSY theory. So the pre-SUSY theory is richer, and the SUSY theory computes for you a certain subsector of correlation functions of the pre-SUSY theory.
And you checked this guy does not go to 0 when you said n equal to 0?
No, it doesn't go to 0.
But if you contract indices, let's say I1, I2, then it?
If you contract indices, then it will go to 0. But if you don't contract, then it's something non-trivial.
But from your previous lecture, from understood, it's just consequence that if you could integrate out of a chi, you get some determinant in the power, which is number of scalar field, and number of scalar field minus 2, it effectively behaves like a Fermat. This was
yeah. So there's no contradiction.
So all this correlation function, this rule which we are saying, just rule how you could resemble determinant.
You can view it like this, yeah. Okay, well, for the moment, no breakthrough. Let's keep going. You have some idea, Grisha? So I can tell you why. I can tell you what's wrong with why is that? Yeah.
Is the theory conformal?
At the fixed point, it is conformal.
No. But first of all, if away from the fixed point, it will be conformal at lowest order parameter of the expansion. So you have epsilon-expansion. As usual, breaking of conformality will appear starting from 2 second order Okay. So at one loop, you don't sensitive to the breaking conformality.
No, but you are thinking like QCD if I were precisely at the upper critical dimension where the running is logarithmic. I am not. I'm doing by going to 4 minus epsilon and going to the fixed point, and there I am conformal. Okay. There's no breaking at the fixed point. There is no breaking at any loop order.
My question is more you explain scaling dimension powers of epsilon.
Yes.
So lowest order than epsilon. Just coefficient proportional to the epsilon. You start writing delta equal to canonical delta plus something times epsilon.
Yes.
So the coefficient for the epsilon, it seems to me it should be conformal invariant.
Well, if it's just a coefficient is just a number. Of course, the number is a conformal invariant.
Coming back to what you were discussing, why there is a very peculiar pattern of mixing. Why you don't have mixing of the follower with L1.
Yeah.
So one of the examples that I know of when you have conformal symmetry which prohibits you of mixing primary fields with descendant.
Well, yeah, you could say that perhaps each one of the leaders corresponds to a primary, and then they would not, and followers are descendants. But in fact, that's not really the case. The follower is not really a descendant because the descendant would be another leader. I could consider a leader which is just a derivative of L2. It would still be a leader because it would come from the derivative of the original singlet. I do not have to consider it because it's just a total derivative. It's not interesting for the RG flow. But the descendants move. Let's say the descendant would move here, d mu L2. It would move one level up, but it's not going to be the same operator as the follower. Yeah, but then you would go one level up, so box L2. It will still be a total derivative, so not a very interesting operator. But it's not going to be the same as the leader, as the follower at the level 2. It's going to be a different operator.
So can you remind us the conformal group, the SUSY group you have?
The SUSY group is how it acts?
No, the name, OSP.
The SUSY group, the full SUSY is OSP D/2.
But this is the logarithm part. This does not.
This is not yet the super conformal. This is just the SUSY part. And then if I go to the fixed point, then this SUSY gets enhanced to the super conformal Parisi-Sourlas symmetry. Yeah, I'm not sure. This mixing problem, I don't think it has to do something with conformal invariance. It has to do with it has to do with.
Well, it's there's a sense in which the dimension changes for the followers, but also they're required by the SN symmetry, right? So in this theory, you have manifest SN-1, and then maybe you can ask if you can organize the tower. Like, is there a sense in which the followers are descendants with respect to the rest of the SN symmetry? Maybe that's the question that.
Yeah. This is, of course, all this conjecture that followers don't mix with leaders is based on the fact that everything came from the SN invariant symmetry, and this SN invariant symmetry, it seems to be controlling the realization of this action, but I don't see how it is realized on this action. So in fact, one part of the SN symmetry, which corresponds to the interchanges of phi 1 with phi I, it doesn't seem to be realized in any way on this action. When I go to the SUSY action, it comes back in the form of the SUSY transformations. But here, I'm at a loss.
So just when you said that, what you said before, you mean that if you try to take those supersymmetry transformations and write some version of it with replica indices, it doesn't work?
It doesn't work. I can show you, there's a very simple reason why it doesn't work. Because, if I try to do this in terms of replica, then I do something like that. So, for example, d phi I can try to do a d phi is proportional to some chi. For example, chi 2. I mean, let me pick one chi. Then d chi 2, I can again be proportional to omega, plus or minus sine. I don't know. So the reason why this is not going to work is that if I apply the variation here, it's going to be very nice. If I apply the variation to chi squared, it's going to be very nice. But there's going to be one more term which is going to spoil everything. It's this term which will be obtained by varying v prime of phi. So there is an extra term, which is chi a squared v double prime of phi chi 2. And if I'm working in the SUSY variables, then this term vanishes because of the fact that my psi's are Grassmann fields, and so psi squared is equal to 0. But if I work with bosonic fields, I see no reason to claim that this should. I see no reason to discard this term.
I have a simple question.
Yeah.
So when you go to this pre-SUSY action, you're using particular parameterization of phi's.
Yeah.
So phi 1. Now imagine if I just slightly change parameterization, namely instead of choosing phi 1, I'm choosing another phi with other index.
Yeah.
Then I will get the same action up to the labeling of fields.
You will get exactly the same action. Yeah.
Yeah, in terms of the new fields. But all fields and new fields, they relate to each other by some linear transformation.
Yeah.
Which means that this action should have some invariance with respect to exactly the change of the basis.
Well, recall that this S pre-SUSY action is not precisely this action mapped to the variables, but it is this action from which we dropped certain terms, which were irrelevant. And when you drop these terms, so if you take the full SUSY action and you map it to Cardy variables and you keep all the terms, then it is indeed invariant under these extra transformations that you suggest. And it's very nice, you can check it. It's a little bit non-trivial, but it works. But once you drop these irrelevant terms, it's no longer invariant under these extra permutations.
Basically, you're saying because this field phi and omega have different scaling dimensions.
Yeah. So something escapes me. I don't know how to.
So you lost SM?
Yeah, it is lost in the infrared limit. Because the terms that I needed to restore it, they're irrelevant, so they go to 0. So in the deep infrared limit, you seem to have lost Sn.
I thought you still had Sn, but it acted in some funny way on these fields.
In the intermediate steps of RG flow, it is there, but once you decide to drop the followers and work just with the leaders, you really got rid of Sn, and then you argue that for the RG purposes that's fine, but it's still a little bit unfortunate that you have no trace of it.
Because if you still had Sn, you could say you've promoted Sn to a continuous symmetry, right, for the chi's. And then if you,
yeah.
So then you might think you should have a larger continuous symmetry, which involving the other component.
Well, continuous symmetry on chi's is just the rotation acting on chi's, but that doesn't help.
But when you have continuous rotation on some of the components, but why not? What's a priori? There's nothing special about those components. Okay, if you lost the Sn, then.
Yeah, no, but here really Sn is not visible in this Lagrangian. So you see the problem. Anyway, let's. If one of you has any ideas, we can discuss maybe after the lecture in the break. So now I would like to go to a second topic, which is very different from this, which has to do with branched polymers. I discussed in my lectures the random field Ising model, but the branched polymers is a related problem in theoretical physics, which has to be discussed in parallel and which has a lot of analogies. And I would like now to briefly discuss what these analogies are. So let me tell you what are the branched polymers. So a polymer in general is, you can think of it like the usual polymer. You can think of it made out of monomers, which are just some rods of a fixed length, and then you connect these monomers at vertices, and they can form certain angle. You know, you have this chain of monomers, and then you impose a constraint that that the two different vertices, they are not allowed. So there is some repulsive potential which does not allow these polymers to collapse, to glue together on two different vertices to come close to each other. So there's some repulsion. And this means that if you go to the continuum limit, then the statistics of these branched polymers is the same as in mathematics an object which is called self-avoiding walk. So this normal polymers are analogous to the self-avoiding walk. While branched polymers they are like the usual polymers, except that they are made of several branches which are allowed to meet at points. You know, you can have things like that. Right? And so you allow these vertices where the polymer can branch, but you still impose the constraint that the points which do not belong to these vertices, they should still repulse. So there's still some repulsion. And, well, there are some chemicals, there are some molecules which really behave in this way. So you can imagine some molecule which is in some solvent. And because of the solvent, you know, all of these monomers of which the polymer is comprised, they can move around freely, and they can explore all the available phase space. So there is some distribution, and so you can now study the statistics of these polymers, and then you can ask various interesting questions. Like one question that you can ask is, for example, you can ask whether what is the mean radius. So this is called gyration radius. So let's suppose you take a polymer which is made out of n monomers, and you can ask for the radius of the polymer as a function of n, you know, the average radius of this object, and then it's going to go as n to some power, and this power is denoted by nu, which is the critical exponent of the problem. So it's a universal number, and the Hausdorff dimension of this branched polymer is related to this nu as 1 over nu. Another thing that you can ask is kind of, so okay, here I'm considering a continuous model of polymers, but suppose that I discretize this somehow. You know, suppose that I'm only allowing polymers, you know, to move in the vertical and the horizontal direction, things like that. Then you can ask the number of polymers made out of n links, and this number is going to go, depending on the microscopic model, as some constant to the power n times n to the power minus theta, and this theta is also a critical exponent of the problem, so which is also supposed to be universal. And so it turns out that you can study these polymers, you can study the statistics of these polymers, for example, on the lattice, you can simulate them, and so on the polymer, on the lattice, these things are called sometimes lattice animals. People have done it, and there are very good predictions from the lattice of the critical exponents nu and eta for all d. The interesting range of d is from 2 to 8, because 8 is the upper critical dimension of this problem. Now, why am I telling all this? So far, this problem has really nothing to do with random field Ising model. Because there is no disorder, there is some geometry involved. While for the random field Ising, there was statistics and disorder. However, it turns out, that it was found in 1981 by Parisi and Sourlas again, who were based on some previous work, I think from '78. From Lubensky and Isaacson, that this problem is very closely related, in fact, to the problem of random field Ising model. So what these guys found is that they found a field theoretic description for the problem of branched polymers. So they found a field theory. And the field theory for the branched polymers turns out to be exactly the same as the replicated action for the random field Ising model, except that you are supposed to take the potential V of phi, not quartic potential as we were taking for the random field Ising model, but we are supposed to take a cubic potential. So m squared phi squared plus with an imaginary coupling I lambda phi cube. So this goes through some lattice mumbo jumbo. You know that the limit n going to 0, for example, appears already for the theory of polymers, where you go to self-avoiding walk. It's the Dejean story who said that the phi to the 4th theory in the n going to 0 limit describes self-avoiding walk. So here actually the n going to 0 limit appears not because of the self-avoidedness property, but for another reason, because we want to consider diluted polymers. We want to consider just a single polymer. But nevertheless, they found this map. And based on this map, using the same bag of tricks that we discussed in the second lecture, they made a prediction that also branched polymers should show dimensional reduction. That the critical exponents for the branched polymers, nu and eta, they have to be equal to the critical exponents of another field theory model in d minus 2 dimensions. And what is this field theory model? It's a cubic potential with an imaginary coupling, and this is the well-known the Li-Yang universality class. So they argued, based on this, that there should be dimensional reduction to Li-Yang in d minus 2 dimensions. And for the Li-Yang universality class, there are very good predictions of critical exponents based on exact results. So there are exact results for, so let me denote this d minus 2 d hat. So if d hat is equal to 0, 1, or 2, there are exact results for the Li-Yang. And if d hat is equal to 6 minus epsilon, there is epsilon expansion for the Li-Yang. So basically, the critical exponents of Li-Yang are very well known. So we have good critical exponents from the theory side for Li-Yang. We have simulations for lattice animals, and they perfectly agree for all d between 2 and 8. So the situation is dramatically different from the random field Ising model. Random field Ising model, we saw that the supersymmetry only holds perhaps in 5D and close to 6D, while here the supersymmetry seems to hold for every D.
So this imaginary I, you need in order to have -1 sign. Why should be imaginary coupling? Just have -1 sign if you have an even number of vertices.
Well, initially you have it real, but then you land on some action, on the same action where this delta parameter is negative, and then you want to have to compare with the previous story. You want to have delta positive, and then it amounts to the change of coupling. And so actually this puzzle, this difference between branched polymers and random field Ising model, it kind of makes the whole problem of Parisi supersymmetry sharper. You know, now you not only do you have to explain why the Parisi-Sourlas supersymmetry is lost for the random field Ising model. If you believe that you found a mechanism by which the supersymmetry gets lost, then you better show that for the branched polymers, the same mechanism does not predict that the supersymmetry gets lost. And you know, this problem was of branched polymers was famous, was well known. But unfortunately, there is, I found out that there is a considerable confusion about the status of this problem in the literature. And this confusion is caused by a famous paper by mathematical physicists, by Bridges and Imbri, who in 2003 wrote a famous paper. It's published in Annals of Mathematics, so a top mathematics journal. And well, let me first tell you what they did, and then let us discuss what should be the lesson, what should be the take-home message. And then you will see where the confusion arises. So Bridges and Imbri, they considered a very particular type of the branched polymer. So in the general branched polymer, there are two effects. So there is like a rod, right? And you know, in a simple model, this rod may have a fixed length, but perhaps you can consider a model of branched polymer where this instead of having a fixed length rod, maybe you would like to introduce some distribution factor for the distance, and let me call this distribution Q of R. This could be some general function. So that's one effect. And then there's another effect which tells you that if we have two vertices which are not joined by a rod, then there is a certain repulsion potential. And this repulsion potential we can describe by another factor in your path integral, in your configuration space integral, which we call P of R. And this P of R might have the following form, you know, which just tells you that if the distance, so this is like P of R, typical form P of R, which says that if the distance R is very small, then this factor P of R is 0. That means that those configurations are going to be suppressed. And if the distance is large, then this factor P of R is 1, and it means that all those configurations are allowed. So a general model of branched polymers is going to be characterized by these two functions, Q of R and P of R. And so Bridges and Imbri, they considered a particular model, a particular class of models of branched polymers where these two functions were related by this formula, Q is equal to P prime. If you look at these two functions, you see that in principle it is compatible to pick Q equal to P prime. This more or less corresponds to the shape that you would like to have. And what they showed is that in this particular case, Q equals P prime, the partition function of branched polymers has exact supersymmetric representation. So from this case, they found exact SUSY. You know, this relation Q of P prime, it comes about by like basically saying, taking P, and you know, we had these relations like this. If you write things like x squared plus theta bar theta, and you expand in theta bar theta, you will get another function which is going to be the derivative of P, and that's how Q comes about in their construction. And so, because in this particular case, there was exact SUSY, they were able to show that the partition function of this particular class of models of branched polymers also has exact dimensional reduction, which should not be surprising. We argued that SUSY implies dimensional reduction. And so exact SUSY, so exact dimensional reduction, and exact dimensional reduction to what? Exact dimensional reduction to a gas of particles in d minus 2 dimensions with negative fugacity. With negative fugacity. So by fugacity, what we mean by fugacity is that normally when you take a partition function of in the grand canonical ensemble, you take a sum over n, 1 over n factorial, and then there's a factor z, small z to the n, which is times something else, and that's the fugacity. So in the physical situation, this is related to the chemical potential, and it's positive. But in this case, when you do this mapping, you map on this sort of expression, but z is negative. And so if you take a partition function of a gas with positive fugacity, then it's just a non-singular function of fugacity. But if you make analytic continuation to negative fugacity, it's known that this partition function of a gas with repulsive interactions has a singularity. And it is believed that this singularity is in the universality class of the Lee-Yang model. So this is believed. So at z equal minus z critical to be equivalent to Lee-Yang. So this they don't prove, because this is hard to prove, but so the main point of the result is to show this exact SUSY and the exact dimensional reduction. And so that's all and fine, but the conclusion arises is that somehow people mention this result and say that Bridges and Imbri proved dimensional reduction, that the dimensional reduction for branched polymers is always there. Of course, they did not prove that it's always there. They proved that the dimensional reduction holds for this particular class of models of branched polymers, which have microscopic built-in supersymmetry. Now, this becomes almost a circular argument. The whole problem of establishing dimensional reduction is to show how supersymmetry emerges at long distances. If you start with a model which already has a built-in supersymmetry at the microscopic scale, well, then it's not so surprising that this model is going to have dimensional reduction of critical exponents. And the result of Bridges and Imbri doesn't say anything about what happens if you depart from this relation Q equal P prime. So this problem is to say what is happening when you depart from Q equal P prime is completely open as far as I know from mathematical point of view. And from the physics perspective, this problem was studied by my collaborators Emilio and Apertim So what happened is that we first studied the random field Ising model together, and we found all this picture that I described. And then Emilio and Dapertim, they went to see what happens with our theory if you apply it to the branched polymer case. They would like to, they wanted to see if somehow for the branched polymer case, for the phi cube potential, you can apply exactly the same theory as I described for the random field Ising model. You map to the Cardy fields, you describe the leaders, followers, you study the anomalous dimensions, and you can ask the following question. Well, are there any operators in that case which have negative anomalous dimensions and can become relevant? So, of course, the details of the computations change because you have now different interactions, phi cube vertices instead of phi to the fourth, imaginary fixed point coupling. So the signs of anomalous dimensions may be different. And in their work early this year, they showed that for the branched polymers, there are no operators which have negative anomalous dimensions. So all operators that they found, they had positive anomalous dimensions. And so there is no destabilizing effect which could break supersymmetry. So that was a nice test of our scenario. So that.
What is the open problem?
Well, the open problem is that, I don't know, in the first lectures there were some mathematicians in the room. Are there still any mathematicians left? Maybe not, but if there are any, I was just wanted to emphasize that it's still an open problem in mathematical physics to show that there is dimensional reduction for branched polymers away from the SUSY case considered by Bridges and Imbri.
Does it make sense to do perturbation theory in the model if you slightly changed?
It could be, yeah, it could make sense to do this calculation, but this has not been done to my knowledge.
So just to understand, if you start from these configurations, then quantum corrections will not drive you away from this. Is it correct to say?
It is correct to say this. It's a stable.
So, but then if I imagine I will start with potential, which will be I lambda phi to power 4. How important was power 3? The reason I'm asking is that
Phi 4, yeah, you can consider, but what is important is that this interaction is the most relevant one. So you can add phi to the fourth, but phi to the fourth is going to be less relevant compared to the cubic. So it's the cubic one which is going to determine the infrared dynamics.
I understood what you want to say, but in the previous case, you had a potential which was 5 to the 4.
Yeah.
Now imagine I will start this previous potential, but put I in front of the coupling constant. My question is that in the first case, you said that this relation will be broken by the quantum corrections.
Which relation?
Supersymmetry of a theory will be broken by quantum corrections.
Not by quantum. Supersymmetry is going to be broken by. You see, in the random field Ising model, there's a big difference between random field Ising model and branched polymers. In the random field Ising model, the supersymmetry is always broken at the microscopic level. So in your fundamental Lagrangian of the random field Ising model, there are always some effects, perhaps small ones, but there are always some effects which break supersymmetry. And so you need to understand what these effects are going to do in the infrared. Are they going to grow or are they going to go to decrease? In the branched polymer, there is an amazing thing that there is a model of branched polymers which realizes supersymmetry exactly at the microscopic level. That's a big luxury that doesn't exist for the random field Ising. And of course, if such a model exists which realizes it exactly at the supersymmetry, then there are no effects which break supersymmetry, then this is completely preserved by RG. So.
There's a different class of models where you can introduce fermions on the lattice, not the full supersymmetry, but by starting with the polymer and then deflating it in 2D. With negative pressure inside the polymer, and then the linear polymer collapses into the branched polymer with like a double strand.
And it also gives a SUSY description.
You can introduce the Grassmann variables, but okay, you don't have microscopically the Parisi-Sourlas.
Yeah, but maybe you have a subgroup of Parisi-Sourlas. Because also bridges Imbri, they don't have, of course, full Parisi-Sourlas because you cannot generate. I think they have a subgroup, but that subgroup is probably enough to kill. So even models which generate only a subgroup are also interesting.
Do you have some intuitive way of understanding why in the branch polymer it works and in the Ising model it doesn't?
Yeah, why for the branch polymers there are these models, there are these interesting models which generate.
Why these perturbations are irrelevant rather than relevant, or?
You mean for the case without SUSY, for the case when we don't assume SUSY from the start? No, we don't understand it at an intuitive level. It just comes out of a computation. There is a bunch of diagrams. Signs are different. In one case you have real coupling, in another case you have imaginary coupling. Terms are proportional to the coupling squared. That could be a naive reason, but there are also some factors over the one which have to work out correctly. So, yeah, I think we don't really understand. So, yeah, so then there is another thing about branched polymers that I want to mention because we discussed this with Adam the other day. So there is a paper. So there is a question whether this problem of branched polymers has conformal invariance or not. So there is a paper by Miller and De Bell. I think sometimes in the 90s. They studied branched polymers in 2D, and you can study the branched polymers in 2D. It's a two-dimensional theory. It was in the 90s, so in the 90s, of course, people were very interested in conformal field theories, in two-dimensional conformal field theories. So they wanted to see whether these branched polymers had the conformal invariance. And they found that it does not have a Virasoro invariance. So what they found is that the branched polymers in 2D, there is no Virasoro. And somehow they made a big deal out of it. But I just wanted to point out that even though there is no Virasoro, but there is still a global conformal invariance in any D, as far as I know. And so, for example, in D equal 2, there's still going to be invariance under Möbius transformations. And if mathematical study of branched polymers is going to be performed at the same level as people study self-avoiding walk in 2 dimensions, they should still be able to see this Möbius invariance in D equal 2.
But if you have Möbius invariance equal to, how could you not have a Virasoro?
Good question. So there is a so of course everything is controlled by the trace of the stress tensor, and so there are various conditions on the trace of the stress tensor. If the trace of the stress tensor is equal to the divergence of some current, then we have scale but no conformal, not even but no conformal, not even global conformal. If we have the trace is equal to the box of a scalar, then in this case you can improve the stress tensor and you can get that the trace is 0, and in that case you get Virasoro. But if the trace is equal to the divergence to the double divergence of some 2 tensor in 2D, then this is enough for Möbius. You can check. It's enough for Möbius because of these 2 derivatives, but not enough for Virasoro. Because in 2 dimensions, given such a trace of the stress tensor, you cannot improve to T mu equals 0. So that was studied long ago in a paper by Polchinski. These improvement conditions. So there is no real puzzle. This theory is conformally invariant, but just in a restricted sense. So this should be kept in mind for whoever does mathematical theory of these things.
So when people say scale implies conformal in 2D, this is what they really mean, that you can always get global, that somehow unitarity is what buys you Virasoro usually. Because most CFTs that we know, unitary CFTs, they always have Virasoro symmetry, right?
Unitary CFTs have Virasoro symmetry.
All the examples.
By CFTs, you mean CFTs globally invariant CFTs? Yeah, because if we are in 2D and the theory is unitary, and if it satisfies this equation T mu equal d mu v mu nu, then you can ask, what is this guy v mu nu? What is this operator? And if it's really a 2 tensor, then it violates unitarity bounds. This equation cannot be realized in a unitary theory. Okay, so that finishes the second topic I wanted to discuss. And I go to the third topic, which is non-perturbative RG. Is there someone working on non-perturbative RG in the room? I'll tell you what I know. So let's go back to the random field Ising model. And in many papers starting from 2004, there was a work by Tissier and Tarjus who applied non-perturbative RG to the random field Ising model. Now, what does it mean, non-perturbative RG? It means that you make a certain physics-motivated ansatz for the effective action of the random field Ising model, working, for example, in the Replica formalism, and this ansatz includes many couplings, allows for many couplings, and then you look for fixed points within this ansatz. And it's known that this method often gives good qualitative understanding of fixed points in various dimensions, for example, for the Ising model. Even if it's maybe not super rigorous, it's still a valuable tool to exploring the phase diagram of various models. So it's interesting to ask what this method gives for the random field Ising model. And these authors and their collaborators, in many papers, they found that there exists a change of regime in the realization group equations for D less than d critical value, which is about 5.1. So in particular, they noticed that for d less than d critical, they noticed that, okay, let me call it change of regime, because the way they detect this change of regime is that certain functions which they solve for, they, instead of being smooth and analytic, they become non-analytic when you go to d less than dc. But also they notice that supersymmetry, certain relations of critical exponents which are implied by supersymmetry, they get broken in this regime. For example, they find that eta, there are these two exponents, eta and eta bar, which I introduced in previous lectures, which have to be equal in supersymmetric theories. And they found that if they are indeed equal, if d is larger than d critical, and not equal for d less than d critical. And so, you know, I don't want to focus too much on the fact that they predict the d critical equal to 5.1, while from our calculation it comes out to be 4.6. That's not really the point, because both our method and their method have certain uncontrolled approximations. And it's not really reasonable to insist, at least at this point, at the precise value of d critical. So a priori, there could be a nice agreement between what they did and what we did. But actually, if you look a little bit more carefully, then there is then it doesn't really match. You know, so our conclusions and their conclusions, they don't really match in certain aspects. And that really represents for me a puzzle that would be interesting to clarify. So what doesn't match? The main thing which they claim the following phase diagram. So they claim that as d varies, for d larger than d critical, there are two supersymmetric fixed points. So there are two SUSY fixed points. Which annihilated d critical, and somewhere here, out of this point, there emerges another non-SUSY fixed point, which is the one that controls the physics of the non-supersymmetric random model, random field Ising model. And now, the reason why I draw these pictures like this is that they, from their calculations, also all quantities near this d critical have a square root singularity behavior. Like critical exponents that they compute from their formalism, they have square root singularities in critical exponents. And okay, so that's what they predict, and that's clearly not what we predict, because we say that well, we have one supersymmetric fixed point above 4 dimensions, above d critical, not two supersymmetric fixed points, and also we don't have any square root singularities, you know, when we go below d critical. And the reason why we don't have those singularities is that because we, looking at the symmetry structure of the terms that become relevant and break supersymmetry, you know, since those terms break supersymmetry, they are not of the same symmetry as the supersymmetric action. They have different symmetry. And when the couplings which become relevant, they do not have the same symmetry as the Lagrangian that you break, then typically you don't expect to have these square root singularities. While the classic example when you do have square root singularities is indeed fixed point annihilation. So fixed point annihilation leads to fixed point annihilation indeed gives this sort of square root singularities. And there are famous examples where this fixed point annihilation happens. And so the famous example is the Potts model, is the Q-state Potts model. For example, in 2 dimensions, if you take Q-state Potts model, then as a function of Q, this model indeed has 2 fixed points for Q less than 4. One is the critical and one is the true critical Potts model. So this kind of theory space on the vertical axis. And then at the Q equal to 4, these fixed points annihilate. This indeed can happen. So if you have 2 fixed points which have exactly the same symmetry and they meet, then they can annihilate and they can go to the complex plane. This can happen. This happens for the Potts model. But after this happens, you don't find any fixed point on the other side of the phase diagram. Because the annihilated fixed points, they went into the complex plane. And this is actually very easy to understand from the point of view of the beta function. So what happens is that your beta function, has 2 zeros, and then as you vary the parameter, for example q, then these 2 zeros they coalesce, and then later on the beta function just goes further up, and the fixed points completely disappear. So what I want to say is that in the examples that I'm familiar with, that are classic examples of renormalization group theory, when the fixed points annihilate, nothing is left. And I'm not aware of any example where 2 fixed points annihilate and then a third fixed point just splits off at precisely this moment. This is really the only case that I'm familiar with where such a behavior is claimed. And it's not obvious to me how to accommodate this behavior with the basic principles of renormalization group. But this is a puzzle, so I would like this to be clarified.
So one of the fixed points supposedly is the same that you are considering, the SUSY one, but the other one, do you know what it is?
I have kind of an idea about what it is, and I wanted to discuss this a little bit later on. But even the one that I understand what it is, it wouldn't have this square root behavior, and it wouldn't annihilate, because it wouldn't have exactly the same symmetry. I don't really know of a SUSY fixed point having exactly the same symmetry. So the SUSY Lagrangian that I was writing, the Parisi-Sourlas Lagrangian, I mean, if you just focus on this SUSY Lagrangian, it only has one fixed point, which is the one which naturally projects to the Ising model in d-2 dimensions. We know that the Ising model only has one fixed point, so...
I thought there is a statement that fixed points which have different symmetry should not should cross somehow.
Yeah. It seems to run against this basic intuition. So there is this big difference between our scenarios, and it would be nice to resolve it, but there is also perhaps a simpler way to distinguish these 2 scenarios, their scenario and our scenario, which it could be done by doing numerical simulations in 4D. So according to their scenario in 4D, there is just the non-SUSY fixed point. So the SUSY fixed points, they really annihilated, they disappeared. They don't exist in 4D. Why, according to our scenario, recall I was drawing this sort of diagram where the SUSY fixed point existed in any D, and it was just becoming unstable for D less than D critical. So this is our scenario. And so it means that if you go to D equal 4, it should be possible to perform some tuning in the numerical simulations, and it should be possible to see this supersymmetric fixed point. And so if this supersymmetric fixed point is really seen, then it would be definitely, it would allow us to distinguish these two scenarios. And that's the last thing I wanted to discuss. Yeah.
How do they get this scenario with two true fixed points in the same dimension from the non-perturbative RG?
Well, I think it's very difficult to say how unless you have done these calculations. I studied their papers. They say that's what comes out of their calculations. But I haven't checked, I haven't run their code, I haven't looked at their equations. There is something else which is a little bit, which I find a little bit strange in their way of approaching this problem, is that they have two ways to recover this picture. One way, which is just by working with the replicated action, and that should be probably perfectly fine, as far as I'm concerned, because this is just from the first principles. And then they have a second way which supposedly leads to exactly the same picture, although I'm not 100% sure, which proceeds as follows. They say they take the Parisi-Sourlas supersymmetric action, and then they replicate the Parisi-Sourlas supersymmetric action once again, and then they put into the Parisi-Sourlas supersymmetric action some extra terms which are motivated by some physics arguments related to the fact that the stochastic differential equation may have different solutions, so it would be nice to suppress some of those solutions. And so out of this very complicated action, which comes from double counting, because Parisi-Sourlas action is already obtained from this, as we have seen, from the replicated action in a certain limit, but they replicate it again, so this is double counting, plus they put on top this term which is not from first principles but physically motivated. They claim that they can also derive the same picture and exactly the same value of the critical. So how does this come is a little bit of a mystery to me, but hopefully I'll be able to talk to them and find some common points. So for the moment it's good to reserve the judgment. And let us look on the positive side. How could we try to confirm our scenario through the Monte Carlo simulations? Monte Carlo or numerical simulations. It's really the last topic. So tuning. So how to tune to the SUSY fixed point in D equal 4. So remember that we identified two operators which become relevant. So one is the leader of F4, which is chi² squared, and another which is the leader of F6, which is chi³ squared minus 3/2 chi² chi to the 4th. So how do you tune? Well, one way of tuning is to vary the disordered distribution P of H. So recall that as I was describing in the first lecture, when people do numerical simulations, they do them at 0 temperature, and they pick this disordered distribution P of H. For example, suppose you pick a Gaussian distribution. Pick any distribution f of H. then you have to vary this distribution already. So in fact, what you have to consider is that you have to consider P of H equals kappa squared f of H over kappa. No, what I'm saying. So 1 over kappa, sorry. So what you are doing is that so this kappa parameter measures the strength of your disorder, and to get to the phase transition, we have to so suppose that you fix some distribution f of h, Gaussian. Then you have to, by this sort of rescaling, you have to find k kappa going to kappa critical in order to find the phase transition. That's the first thing that you should do for any disorder distribution. So that's already one variation of P of H that you always have to do. But suppose that on top of that, on top of that, you find some other variation. So you find some family of distributions Ft of H, which, for example, varies between Gaussian distribution for t equals 0 and maybe double Gauss, something like double hump distribution for t equal 1. Suppose that you do something like that. So for each of these distributions in this one parameter family, you find a critical point and you study critical exponents, and so that's something that in numerical simulations people tell me that they can do. So how can we theoretically think about this situation in terms of tuning? Well, the way we can think about this is that we have an effective action at the critical point, which is the pre-SUSY action plus these two operators that we are considering, G1O1 plus G2O2. And each of these couplings, G1 and G2, they depend on T. And to find a SUSY fixed point, you would like to tune both of these couplings to 0. But of course, you cannot tune both of them to 0 if you just have a one parameter family of distributions. And people who do simulations, they don't want to consider two parameter families of distributions because it's too complicated. So we have to understand, okay, is there any chance to see SUSY if you only have a one parameter family of distributions at your disposal? That's what I would like to discuss.
What if you only have one relevant deformation, therefore one of them will be automatically tuned?
Well, but we have seen in results of our anomalous dimension calculations, they show that this both of these operators, they cross the relevance barrier between 4 and 5 dimensions. So by the time you are down to 4, they are both relevant. So somehow you have to deal with both of them. Of course, those calculations have to be done more carefully, and maybe in the end of the day, one of them is no longer going to be relevant. I don't know. But let us take at least the current results at face value and see what is the picture.
This is in addition to the mass, right?
Yeah, this is in addition to the mass. The mass has been tuned to 0 by the kappa. So actually, well, how are you going to go around this problem? So we are in D equal 4. So let us write down, let us first of all forget about G1 for the second. So G1 corresponds to the SUSY null coupling, and as you recall, the SUSY null coupling, it's not as dangerous as the SUSY non-SUSY writable one because it doesn't really break SUSY by itself, because the SUSY null coupling does not have any effect on the SUSY sector of the theory. It can only have this effect indirectly by changing the dimensions of the non-SUSY writable operators. So let us forget about G1 for a second and see what to do with G2. So for G2, we write a beta function equation. So we write the beta function of G2. So running from UV to IR. The beta function for G2 is going to be some positive constant times G2. So this coupling G2 is relevant. So this constant is proportional to d critical minus d. So and d is 4. Plus there's going to be some other term which is going to be quadratic in G2, which is proportional to its own constant B2. So what is this constant B2? What do we know about it? So this constant B2 is related to the OP coefficient to the 3-point function O2, O2, O2 computed in d equal 4. And we don't know what this 3-point function is, because we only have done a computation for the dimension of O2, but we haven't computed how this 3-point function varies as a function of d. So this is a separate computation that one could in principle perform, but we haven't performed it. But what we can try to do is that we can try to borrow this result for this 3-point function starting from d equals 6. So let us suppose that let us replace this B2, which has to be computed in d equals 4, by its value in d equals 6. That's just an approximation, but now you can do a calculation because O2 is an explicit operator in terms of chi's. You can compute its 3-point function coefficient. It's a well-defined computation, and you actually find that this B2 is a positive constant in d equals 6. Positive, meaning that it has the opposite sign from the phi to the 4th, from what it would have for phi to the 4th theory. And so what does this mean? It means that if G2, if the initial value of G2 is positive, then G2 just flows to plus infinity. And so this would correspond to a first order phase transition. And if the initial value of G2 is negative, then G2 is going to flow to a fixed point, which is equal to A2 over B2, minus A2 over B2. So the beta function has this form. And so you have the supersymmetric fixed point, of course, where G2 is 0, and you have this non-supersymmetric fixed point where G2 is negative. And you have this RG flow. And this supposedly leads to a first order phase transition. That's the simplest assumption. Now, is this a problem that the fixed point coupling G2 is negative? I don't know. So recall that this operator F6, it was appearing, it looked like phi I minus phi j to the 6th in the SN invariant theory. So is it a problem to have such a coupling in your effective action with a negative coefficient. If this was a real theory, if this was a normal theory, I would say, yeah, this looks problematic. But since this theory has an n going to 0 limit, then perhaps this is not so problematic.
So if G2 is negative, potential goes with plus coefficient. So from point of view of, so you have a theory which has certain potential.
Yeah, the potential is bad, has a bad sign, wrong sign.
But you think if G2 is negative, this goes directly into potential?
Yeah, this goes directly into potential, yeah. It's bad, looks bad. But the theory has n going to 0 limit, so maybe it's not so bad. Or maybe this 3-point coupling changes its sign and then it's not so bad. So we are, putting question marks on top of question marks. But in principle, that's the logic you are supposed to follow. Let's just try to make the best of the information we have at our disposal.
No, but if at the moment the potential turns sign, then you expect whatever the expression will be right, it will become very unsummable. It's the standard argument about Dyson via QED for negative coupling constant is the same.
In a normal theory with an integer number of fields, yes. In a theory with 0 fields, I don't know. So we are a little bit on shaky grounds here. So now let us look at G1. So for G1, in principle, we do the same thing. So again, we write the beta function for G1. We have again A1 G1 plus B1 G1 squared. Again, A1 is positive, and B1, again, you can compute it, and in this case, it turns out that it's negative in d equals 6. I hope I didn't make a mistake, but that's the calculation that one can do in principle. And so in this case, the beta function has a different form. So it looks like this. So it's beta 1, G1. And so here we still have this fully SUSY fixed point at the origin. And then if G1 is small and positive, then it will flow to this fixed point. And if G1 is small and negative, it's going to flow to minus infinity. Now, if G1 flows to minus infinity, then I don't really know what happens, because G1 by itself, it doesn't do much to the SUSY theory. But if it flows to minus infinity, it can wreak havoc. It could do whatever. If G1 flows to this fixed point here, which is going to be at some value equals A1 over B1, minus A1 over B1, then in principle, if this G1 star is not too large, then I'm in a strange situation. So it could be that perhaps this point has the right to be called a supersymmetric fixed point, because G1 has flown to a small fixed value coupling. Suppose that this fixed point value is not too large, so it did not really change the scaling dimensions of other operators by too much. All the supersymmetric correlation functions are not affected. So if people, all the correlation functions that people measure in the numerical simulations, they measure the simplest type of supersymmetric correlation functions. Those correlation functions are not going to be affected by the presence of this value G1. So they are in that simulation, they are still going to see supersymmetry. They are still going to see dimensional reduction for that class of correlation functions. Okay, so now let us put, so I could call this perhaps pseudo-SUSY fixed point, I don't know. Or how should I call it? Well, let me call it pseudo-SUSY. No, I mean, it's not really broken, because the observables that were SUSY, they remain SUSY. So it could be, it's really SUSY. It's really, maybe I should call it SUSY prime. There are two supersymmetric fixed points. and they are very difficult to distinguish. It would be very difficult to distinguish in a numerical simulation, because they would only differ by correlation functions involving non-supersymmetric observables, and those correlation functions, they are require measuring 4-point functions at least. So it's a complicated measurement. And so now let us put these things together. So we have picture for G1 and we have picture for G2. So if you now put this together, both couplings, G1, G2, we have a cross term, because so G1, when you run RG, G1 G1 cannot generate G2, but G2 can generate G1. So there's going to be some coupling, some term here, which is proportional to G2 in the beta function for G1. So what's going to happen is this. It's not a good picture. I should leave more space below. So G2 positive, as we said, is going to be first order. Then on the line G2 0, we have two fixed points. We have which are both SUSY. So this whole line corresponds to SUSY theories, and here, here it's something. It's not necessarily SUSY. We don't know what it is. And then at negative G2, we have two fixed points. One which are both non-SUSY. So we have kind of a flow diagram like this. We have this, maybe this. So we have a total of 4 fixed points. Two SUSY ones. Let me call it F SUSY 1 and F SUSY 2, and two non-SUSY and two SUSY breaking ones. And this is the most stable one. So let me put it. So this one is the most stable. So the claim would be that if you just do a numerical simulation with a randomly chosen distribution P of H, you either see this F SUSY, or you see a first order phase transition, or you see some other stuff which is in this part of the diagram, which may house some other fixed points, but I'd have nothing to say about them. Complicated stuff. So let us suppose that this is the non-SUSY fixed point that they see in normal numerical simulations when they do not perform any SUSY, any tuning. And let us suppose that we are now going to do some tuning. What is going to happen? So if you find, suppose that the first option is that your tuning is going to correspond to some trajectory in this plane. So you vary this. You vary these parameters G1 and G2 in some way that you don't really know, you don't really control, because you vary your microscopic distribution P of H, but it's an extremely hard problem to guess what this translates to in the variation of couplings G1 and G2. You cannot really solve this problem, so you just guess. Like guess number one, option number one is something like this. What are you going to see in this case? Well, what you will see is that you are going to, as long as you are on the lower part of this diagram, you are going to always flow to the non-SUSY fixed point, and you will see the non-SUSY critical exponents. When you arrive to this point, which is going to correspond to some critical value of parameter t critical, you are going to flow to the supersymmetric fixed point. But it's going to be not the fully supersymmetric fixed point where both couplings are 0, but this F SUSY 2 fixed point where one of the couplings is non-zero, but that fixed point is still supersymmetric, so you should see the supersymmetric values of critical exponents. And if you keep varying this parameter, you should get a first order phase transition. That's what you would argue based on this diagram. But that's not the only possibility. You can be unlucky, and you can, for example, suppose that you vary, you do a variation, and then somehow your curve bends in this direction. This is an option 2. Well, in that case, you know, and maybe then you just go here, something like that. Well, in that case, you will never see supersymmetric critical exponents, because for a while you will always flow back to this fixed point, which is the non-SUSY one. But then at some point you will cross this line. Oh, no, actually, by the time you cross this line already, so here is going to be the critical value, T critical. And then from this T critical thing, you are going, once you cross this T critical, you are going to flow to another fixed point, this F non-SUSY 1 fixed point. So you will see a different values of critical exponents from the usual ones, but they're not going to be supersymmetric. So which option is realized? It depends on how lucky you are. And if you vary even further, then again it becomes a first order phase transition. So, well, or at least you go in the region where there are dragons. So so you see, it's a non-trivial problem to guess what's going to happen based on the incomplete information that we have at our disposal. But fortunately, the group of people who did the numerical simulations for the random field Ising model in various dimensions, in d equal 3, d equal 4, and d equal 5. These are Fitas, Martin Meyer, Picco-Sourlas, and Parisi. They are now repeating these numerical simulations in d equal 4 because they found an interesting region of parameter space which they have not previously explored. And they have some hopes that they have reasons to believe that this previously unexplored region of parameter space, it has a chance to house new fixed points. So they are working on this, and as far as I know, they do not yet have information whether this new fixed point is supersymmetric or non-supersymmetric. So I'm looking forward to the results of this numerical study, which can shed further lights on this ongoing puzzle of the random field Ising model.
Sorry, D1 and D2, which one is closer to marginal? Which one is at D4?
According to our two-loop calculations, G1 was crossing marginality before G2, but just a little bit prior. So I think that's a good moment to stop this lecture. So we are going to look forward to the numerical simulations and see what's going to come out of them.
Do we know anything about these non-SUSY fixed points? Or these are just some crazy, strongly coupled?
Well, we know their critical exponents from numerical simulations. We also know their descriptions in terms of this non-perturbative RG, even though we sense that something there, is a little bit unusual from the RG perspective. It still provides a certain description of these fixed points, but we are not able to identify these fixed points with any other fixed points that we know of.
These two SUSY fixed points resemble in some way the one of the non-perturbative RG.
Yes, yes. So indeed, this existence of these two SUSY fixed points is a little bit similar to what they saw in the non-perturbative RG. However, because the breaking from one to the other was done by this SUSY by this SUSY null operator, you cannot view these two fixed points as really two fixed points which can annihilate. In fact, these two fixed points, the SUSY sector of these fixed points is just completely identical. So the anomalous dimensions of SUSY operators are going to be equal to these two fixed points. So these fixed points have a common subsector, and only there is a sector of SUSY null operators which is different. While for their theory, as far as I understand, they claim that there are really two fixed points which have different values of SUSY operator dimensions. That's pretty different.
Sorry, if you start from a SUSY fixed point, you turn on a coupling which is SUSY null,
Yeah.
it will run, but it never breaks SUSY.
It never breaks SUSY, and it runs to its own fixed point.
I see. So this would be precisely T1.
Yeah, this would be this F SUSY2, what I call, yeah. So even though it superficially looks similar, but if you look a little bit deeper, you see that it's quite different actually. Well, thanks for attending these lectures, and thanks also for making today's lecture particularly lively.